Alrighty, welcome. Today we're going to talk about the early history of the atom. And by history of the atom, I don't mean the individual life story of any particular atom. I really mean the history of the development of the model of the atom, which we now use to describe all matter and really all the universe around us. Because back in 1800, scientists didn't really know anything about atoms. They weren't really considered a useful model of the world. And because of that, we couldn't really describe what matter was made out of. But we did know a few things about chemical reactions and a few things about elements. And one of the essential tenets of this early chemistry was something called the law of definite proportions, or Proust's law. But before I describe or define the law of definite proportions for you, I want to give you an example of what it means, what its repercussions are. So say scientists in around 1800, say Proust himself, took 23 grams of sodium, and added it to 35 grams of chlorine, elemental chlorine gas. What would he end up with? Well, as you might guess, he would end up with 58 grams of sodium chloride. And this makes sense because elemental sodium combines with elemental chlorine to produce sodium chloride. We've got 55 grams of stuff on this left-hand side. We should end up with we've got 58 grams of stuff on this left-hand side. We should end up with 58 grams on the right-hand side. Okay, that's easy enough. But what happens when we add 30 grams of sodium to 35 grams of sodium chloride? So increasing the amount of sodium by 7 grams. Well, you might expect us to get 65 grams of sodium chloride. We're just adding up these numbers on the left-hand side to get this number on the right-hand side. But that is actually not what scientists found. Instead, they got 58 grams of sodium chloride again, and these 7 extra grams of sodium were left over. So from 30 grams of sodium and 35 grams of chlorine, we were only able to produce 58 grams of sodium chloride. So what this means is that in every sodium chloride sample, we have the same ratio of mass of sodium to chlorine. We've got 23 grams of sodium per 35 grams of chlorine. We could divide these numbers in 2, we could multiply them by 8, we could do anything we want with them, but we're always going to have the same ratio. If we were able to produce 65 grams of sodium chloride from these constituents, well, then that ratio would be 30/35, and that is not what we experimentally observe. We can't have different ratios. And so, as you might be able to guess, what the law of definite proportions states is that a given compound, so in this case we've chosen sodium chloride, always contains the same proportions of elements by mass. The same proportions of elements by mass. And proportions is just a fancy way of saying ratios, and we know our ratio in this case is 23/35. So another way of saying this is that all sodium chloride is created equal. In any sample, we're always going to have 23 parts sodium to 35 parts chlorine by mass. We don't know anything about atoms yet, so we can't describe this as being a 1-to-1 ratio between atoms. We just know it as a ratio between masses. And so that's well and good, but let's extend the law of definite proportions to the law of multiple proportions. Now, the first time I was exposed to this law made absolutely no sense to me whatsoever. But I'm hoping if we work through it and maybe use an example, we can try and make some sense of it. So let's read it first. When two elements combine to form a series of compounds, the ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. Okay, don't panic. Let's break this down. So two elements. Let's change colors. Nice magenta. 2 elements. So say we've got nitrogen and oxygen. 2 elements. Well, we know from the law of definite proportions that when we create a compound, say NO, there's always going to be the same ratio of nitrogen to oxygen. But that doesn't mean whenever we add nitrogen to oxygen, we're always going to get the same compound. Scientists in 1800 wouldn't know about these. We wouldn't know these formulas, but we could get NO2, we could get N2O, we could get N4O, etc., etc. And so when we say a series of compounds, we mean different things produced from the same original elements. And so this example, we're going to take 1 gram of oxygen and combine it with nitrogen to form different compounds. Compound A has 1.750 grams of nitrogen. Remember, they all have 1 gram of oxygen. 1 gram of oxygen. Compound B has 0.8750 grams. Remember, these were experimentally observed. And compound C has 0.4375 grams of nitrogen. Okay, so when we say a series of compounds, we're just referring to these multiple compounds created from nitrogen and oxygen. Look at this next bit. The ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. Well, we've got masses down here, so let's just take a look at these ratios. So, A to C, let's do A to B first. The ratio of the amount of nitrogen in A compared to the amount of nitrogen in B is just going to be 1.750 divided by 0.875. And that, if you do the calculation on your calculator, is exactly 2. Okay, that's good. A to C is going to be 1.750 divided by 0.4375. And that is exactly 4. Alright, what about B to C? Well, B to C is just going to be 0.875 divided by 0.4375. And that is equal, again, to 2. So, when we refer to small whole numbers, this is what we mean. We mean 2, 4, and 2. And so what this is saying is there's exactly twice the amount of nitrogen in A compared to B. There's 4 times exactly the amount of nitrogen in A compared to C. There isn't 1.8749 times the amount of nitrogen in A compared to B, or etc., etc. We always get these nice, easy to work with numbers. And what this perhaps implies is that nitrogen, or any element really, scientists perform similar experiments with lots of different elements and lots of different compounds, is that elements come in little packets. So maybe compound A has 4 packets of nitrogen for every oxygen. Compound B has 2 packets. Compound C, 1 packet. Remember, we're not talking about atoms yet, we're just talking about some packet of mass that is nitrogen, some packet which can combine differently with oxygen to produce different compounds. And so that's what the law of multiple proportions says. It says essentially that elements come in little packets, and when we form different compounds, the ratios of the masses of the elements between those compounds are always going to be small whole numbers because it just reflects the different numbers of packets. But what are these packets? Well, the scientist who is most famous for performing these experiments, John Dalton, formulated a theory of these packets, and he called these packets atoms, as early Greek philosophers had done before him. And Dalton produced a theory, an atomic theory, of mass of atoms with 4 different rules, 4 different laws. And he was doing this in 1808 to give you some context of dates. And we're just going to run quickly through these 4 laws and see if they still hold. Whoops, I forgot an E on the end of Indestructible. Alrighty, number 1. All matter is made of atoms, which are indivisible and indestructible. Well, this part, we know, is right. We know all matter is made of atoms because atoms are the most basic unit of elements, and elements are the building blocks of matter. What about this bit? Are all atoms indivisible and indestructible? Well, we know that inside atoms are protons, neutrons, and electrons, and we know that in certain nuclear reactors, etc., we can break apart nuclei, we can break apart atoms. So this is not exactly true. We've discovered subatomic particles since Dalton's day, but we've got to give him a little slack because he, again, was writing in 1808. Alrighty, so pretty close. Number 2, all the atoms of a given element are identical. The atoms of different elements differ in weight and chemical properties. Well, if you've watched the video on atomic structure, you know that this bit about all atoms of a given element being identical is not exactly true because we know about things called isotopes. Isotopes. And isotopes are atoms with the same number of protons, so the same element, but different numbers of neutrons. And so that means they're going to be slightly different from each other, two isotopes of the same element, with slightly different chemical properties, but pretty much the same, but not exactly identical. What about this next bit? The atoms of different elements differ in weight and chemical properties. Well, we know the weight bit is true because mass number is equal to the number of protons plus the number of neutrons. Remember, the mass of an electron is pretty insignificant compared to the weight of protons and neutrons, so we don't really count those. We know different elements have different numbers of protons because it's the atomic number which defines an element, and we know they have different numbers of neutrons, so different elements, the atoms of different elements, are going to have different weights. And of course they're going to have different chemical properties because we can get anything from gold to mercury as elements, and those things are very different with very different chemical properties. What about this? Number 3, compounds are just combinations of different atoms in ratios of small whole numbers. Well, that bit about small whole numbers should ring a bell. It should sound like the law of multiple proportions. So all this is saying, all law number 3 is saying, is that compounds are constituted of ratios of atoms. Those packets we talked about earlier are just atoms. So this is just restating the law of multiple proportions. All it's doing, restating the law of multiple proportions. And finally, number 4, a chemical reaction involves the combination, separation, or rearrangement of atoms, but atoms are never created nor destroyed. And maybe you haven't studied chemical reactions yet, maybe you have and you're just rewatching this video. I can tell you with certainty that all a chemical reaction is changing the configuration of atoms and moving them into different combinations. And what we can't do in a chemical reaction, unless you're a nuclear physicist studying matter, antimatter, annihilation, is create or destroy atoms. We can't create these particles, and that's why we have to balance chemical equations. We always have to have the same amount of stuff as products as we did in the reactant side of the equation. Another way of saying this is just the law of conservation of mass or matter. We can't create stuff. We can only change its configuration, change its shape, change what it's bonded with to create new kinds of stuff. But the amount of matter, the number of atoms never changes. So that's Dalton's atomic theory, and in the next video we'll take a look at some experiments which took place throughout the 19th century and the early 20th century, which created the coherent model of the atom, which built upon Dalton's early work to create what we now call the building block of matter. I'll see you then.